Good day, everyone. It's a great pleasure to be here with you for another Virtual Axion Institute seminar. I am Azadeh Maleknejad, and I'm a CERN Theory Fellow. Today, I'm going to tell you about SU2-right axion-inflation, which is yet another way that axions can make our physics way more fun. And that's basically about having gauge fields, non-abelian gauge fields in physics of inflation. And this talk will be based on these two papers that you see here. The other one will hopefully appear in a few days. And but in principle, it's basically based on a body of work in the past 10 years, and by me and several of my colleagues and friends. And these last two papers are basically the one that I worked out during the pandemic. So let's see why to even think about SU2-right and its axion in cosmology. So we know that the common puzzles of particle physics and cosmology are the particle physics of inflation, the origin of the matter asymmetry, the origin of the neutrino mass, and the particle nature of dark matter. And for all of them, we basically need physics beyond the standard model. On the other hand, from the cosmology side, we have these curious cosmological coincidences among parameters that shouldn't really be related. One of them is eta baryon, which parameterizes the amount of baryon asymmetry in the universe, which is roughly equal to the curvature power spectrum, which comes from inflation. And also we have the omega dark matter, which is approximately equals 5 times omega baryons. And then talking about the standard model of particle physics as probably the most rigorous theory in the whole history of physics, apart from this issues that we just mentioned, it also faces some other conceptual issues. Of course, depending on who you talk to, they may find these conceptual issues serious or not. I personally think they are serious. And these are basically this ad hoc parity violation in the weak interaction, the fact that we have the SU2 left gauge fields and left-handed neutrinos, but no sign of right-handed SU2 and the right-handed neutrinos. And then we have this accidental B minus L global symmetry in the standard model. We have the problem of vacuum stability and the strong CP problem. The question that I'm going to try to answer in this talk are as follows. First, we want to see what do gauge fields do in physics of inflation? And if they were around, does it come with a cosmological signature so we can test them? And how inflation and its gauge field are now connected to the standard model. And so to be honest, I always, in the back of my mind, I had this question, if there is a simple, elementary, and minimal setup that can solve all of these above issues that we discussed. So about gauge fields in physics of inflation. So we know that normal gauge fields, they act like radiation. So they will decay exponentially during inflation. But if these gauge fields are directly coupled to the inflaton, then during inflation, the inflaton keep pumping energy into this gauge field, and then the gauge field can survive inflation. And as a result, they can be active in physics of inflation. So yeah, gauge fields which are coupled to the inflaton can survive and be active in physics of inflation. And if they were around, it comes with a smoking gun, and that's in the form of chiral, non-Gaussian gravitational waves, which are blue tilted, which makes this the scenarios testable. So now we get to this other question, that how inflaton and this gauge field, which is coupled to it, can be connected to the standard model. So the minimal realization that you can think about it is to extending the standard model gauge symmetry by an SU to right, and then couple it to the axion-inflation. So now, apart from the W left gauge field in the standard model, we also have W right gauge field, and then it naturally extended the 3 left-handed neutrinos in the standard model with 3 right-handed neutrinos as well. And then just to have the most minimal realization, you can simply just couple this W right to the axion. And what is interesting is that this super simple addition has a very interesting consequence, because it can provide a complete beyond the standard model that can solve these issues 1 to 4 in the left-hand side, and these conceptual issues 1 to 4 on the right-hand side. And because it provides a mechanism for simultaneous generation of baryons and dark matter, which is now this the lightest right-handed neutrino, it can also explain this cosmological coincidences. So let us first start with talking about gauge fields in inflation. You may say, oh, why gauge fields in inflation? Well, why not? Inflation happened at the highest energy scales observable to us, and gauge fields are the building blocks of the standard model and beyond, and they are all over the place. So what do they do in inflation? We already saw that gauge fields can actually contribute to physics of inflation. And if they were around, they can leave a robust signature for gravitational wave background. And interestingly, they can change the course of cosmic history, because it immediately comes with a novel mechanism for simultaneous baryogenesis and dark genesis. So the story of SU2 axion models, SU2 gauge fields in physics of inflation first proposed in gaugeflation, which is basically the simple action based on Einstein gravity that the normal gauge fields with Yang-Mills theory has this extra self-interaction in the form of FF tilde squared. And why this term? Because it has the same equation of state as a cosmological term. So if at first, early on, this term dominates over the Yang-Mills, we will have a slow roll inflation. And then this term actually keep sending energy to the Yang-Mills part, which is the radiation sector, and eventually inflation ends in radiation era. Gaugeflation is an effective field theory coming out of a larger theory, which actually introduced shortly after gaugeflation 1 year later, and that's cosmological. And that's basically, cosmological is basically a natural inflation. So we have an axion as the inflaton with a cosine potential. And now the axion is coupled with this SU2 gauge field with a Chern-Simons interaction. And the same story is actually happening similar to gaugeflation. That's the same phenomena happens in cosmological, because now the axion actually breaking the conformal symmetry of Yang-Mills and pumps energy to the gauge field so it can survive inflation and not radiate like decay like a radiation. So far so good, but unfortunately now both the gaugeflation and cosmological are ruled out by the data, and the reason is that in this two setups requires a large coupling between the axion and the gauge field. So for example, in cosmological, this parameter lambda should be very large, and as a result, these setups actually predicting a very large value for the tensor to scalar ratio, which is this observational problem. But at the same time, it brings theoretical issues, because it's really hard to explain this large value for lambda from the theoretical point of view and model building. But based on these two original ideas for SU2 axion inflation, several different models with SU2 gauge field have been proposed and studied. And here we have an incomplete list of these different realizations. But you may ask why so much attention to this SU2 axion inflation. It seems like a very simple idea, but it turns out to have a surprisingly rich, interesting phenomenology. So in particular, it leads to a new mechanism for generation of primordial gravitational wave, which attracts a lot of attention. And on the top of that, soon we realize that all the Sakharov conditions are satisfied in inflation in this setup, and it leads to a new setting. So this ideas are actually a new setting for baryogenesis mechanism and leptogenesis mechanism. The minimal model by which you can actually fix all these issues that I already mentioned about gaugeflation and chroma-natural, this is basically this minimal SU2 axion inflation model, which comparing to chroma-natural, I simply replace the cosine potential with a monodromy potential, and I assume that the potential is flat by itself, so I don't really need a large value for lambda to guarantee slower inflation. So now, if you study the cosmic perturbation in this scenario, it is in agreement with the data and also doesn't suffer this theoretical issue. In this particular SU2 right axion model, we are going to assume that this gauge field, this SU2 gauge field, which is coupled to the inflaton, is SU2 right. So now we are extending the gauge symmetry in the standard model with this SU2 right, and this SU2 right is coupled to the axion. So this is the beautiful left-right symmetric model, which, as you see several giants of particle physics working and building this beyond the standard model. The idea here is that now the gauge symmetry, so imagine that you want to extend the gauge symmetry in the standard model with an SU2 right. Then it turns out that the minimal way that you can do that is to also change the U1 hypercharge with the U1 B minus L. So now the gauge symmetry is basically the SU3 for gluon, U1 B minus L times SU2 left times SU2 right. And that's interesting that we just tried to extended the gauge symmetry with an SU2 right, but it automatically comes with upgrading the global B minus L symmetry with the gauge symmetry. So it can explain that accidental global symmetry in the standard model. And then on the fermionic sector, we're basically having the standard model part, which is extended by 3 right-handed neutrinos. And of course, since we have like extra gauge symmetries to be spontaneously broken, the Higgs sector is an extended Higgs sector. Now on the top of the minimal left-right symmetric model as a beyond the standard model, we're having an axion as the inflaton, and as the most like the minimal realization, we are assuming that only SU2 right is directly coupled to the axion. So yeah, I mean it's super. It seems like a very simple idea, but it turns out that has a lot of interesting consequences. So now, just because we have left-right symmetric particle physics model, it can automatically explain some of these issues that we discussed before. In particular, it can solve all of these conceptual issues of the particle physics, the standard model as a particle physics model. And also it can provide an origin for the neutrino mass because it immediately comes with a seesaw mechanism. And as for the particle nature of dark matter, one can imagine that the lightest right-handed neutrino can be the dark matter candidate. And with this extra interaction with the axion, now we can actually have a specific setup for particle physics of inflation. We can explain the origin of the matter asymmetry, as we discuss soon. And it can provide a new mechanism for generating right-handed neutrinos. And as a result, because it's a simultaneous generation of baryon asymmetry and dark matter, with inflation, like there is a deep connection between inflation, the mechanism for generation of baryon asymmetry and dark matter. It can actually explain these cosmological coincidences as well. And yeah, it is testable because it comes with a cosmological smoking gun. So just to have a better idea about now the gauge symmetry structure, of course we know about this famous weak scale during which all of the standard model particles getting their mass. But now on the top of that, we have this new fundamental scale, which I call field scale. And what's happening is that since our gauge symmetry is extended with this SU2 right times U1 B minus L, after this spontaneous symmetry breaking, it will break to the standard model gauge group. And at this point, the SU2 right gauge field will get its mass, so the W right and the Z right will be massive, and also it will provide mass for the right-handed neutrinos. Sorry, Majorana masses for the right-handed neutrinos, and then eventually at the electroweak scale, now we have all the standard model and on the masses, and on the top of that we have massive left-handed neutrinos because it naturally comes with a seesaw mechanism. Okay, so as for the SU2 gauge field, all of the rest of the gauge symmetries in our setups, they are decaying and inactive in inflation because they're acting like normal radiation. But this SU2 right, which is coupled to the axion, it will get generated during inflation. This is the field equation of this gauge field. And as you see, the effective frequency squared has this funny structure and depend on the sign of the polarization of this mode. It can be plus or minus. So now if this psi parameter is positive, we will have let's call it this red slow roll trajectory, and if the psi is negative, it basically means a negative axion field. In inflation, we will have this blue slow roll trajectory, and that's interesting that based on like the sign of psi, we are actually enhancing one of these polarization states of the gauge field. Now imagine that psi is positive, so the plus helicity state of the gauge field will experience a tachyonic instability phase, which I showed here. So deep inside the horizon, both helicity states plus and minus are basically similar to quantum fluctuations. But when we get close to the point of horizon crossing, this funny term will be large enough so that in the plus helicity state, the effective frequency squared become negative. And you see that the B plus will experience this enhancement phase. And then eventually, after passing the horizon at superhorizon scales, both of them are decay. And now let's go to the fermionic part. All the left-handed fermions, they are exponentially decaying in inflation and inactive because they are massless chiral fermions, and the gauge fields that they are coupled to are not active in inflation. But all the right-handed fermions, they are generated by the SU2 right gauge field because they are coupled to SU2 right. And something magical will happen. The key ingredient is the chiral anomaly of the SU2 right in inflation. And now that, so basically, that's this pink equation. Here, on the right-hand side, we have the W right gauge field, which is non-zero and actually get generated in inflation. So the right-hand side is sizable. And because of that, it can generate baryons and leptons in inflation. The final value for the baryon and lepton number generation by the end of inflation is given with by this relation, when this alpha inflation psi is basically a function in terms of that psi parameters that somehow explain the amount of particle production in inflation by the axion. But remember that all the baryons that we generated are the standard model one. But for the lepton production, part of that is the standard model, and the part that I showed with shaded gray are the right-handed neutrinos. This is a summary of this mechanism from the end of inflation till the electroweak scale. So by the end of inflation, we have equal amount of baryons and leptons, but B minus L standard model is not zero. And that's essential for this baryon and leptons to survive. Then shortly after inflation, this extended gauge symmetry will be spontaneously violated to the U1 hypercharge. And then shortly after, the W right is decoupled, and N1, which is the lightest right-handed neutrino with feeble Yukawa interaction, will also decoupled, and we will have this final baryons, lepton minus lepton N1, which is now decoupled, and the N1, which is our dark matter candidate. And then shortly after that, N2 and N3, which are our heaviest right-handed neutrinos, will decay, and all the spectator effects like this follow rows and the Yukawa interaction will reshuffle this primordial baryon and lepton standard model quantities. And at the scale of electroweak, we will have some final baryon number, lepton standard model, and dark matter. So in a way, in this mechanism, quantum effects in inflation, which is this chiral anomaly of W right, provide a common origin for baryogenesis and cold dark matter. And as a result, it can actually naturally explain the cosmological coincidences. As for the mass of right-handed neutrinos, this mechanism to work requires heavy right-handed neutrinos. Notice that the mass should be higher than 10 to 10 GeV. And then in order for this sterile neutrino to explain the observed value for the dark matter today, the mass of the lightest right-handed neutrino should be around 1 GeV. So now let me just finish my to conclude. Let me just compare the minimal scenarios without this interaction and the SU2 right axion-inflation. Imagine that we are studying cosmology and the dark matter is the lightest right-handed neutrino, so we're extending the standard model by only 3 right-handed neutrinos and no extra SU2 right. And physics of inflation is like the standard one, only made of scalar singlet beyond the standard model. So imagine that an axion is the inflaton, and there's no like clear connections between the physics of inflation and the standard model. Then the prediction is that we will have unpolarized Gaussian gravitational waves because there's nothing to source gravitational waves in inflation. And then as for the baryon asymmetry, a popular interesting mechanism is, of course, a baryogenesis via leptogenesis, in which the source of CP violation is actually the CP violating phases in the neutrino sector. So the idea is that the unconstrained CP violating phases in the neutrino sector are large enough to explain the observed value for the baryon asymmetry. And then as for the mass of these sterile neutrinos, if they are the dark matter candidate, then the prediction is that this mass should be around 10 keV, and it would lead to X-ray radiation by the radiative decay of these right-handed neutrinos. In the SU2 right axion-inflation scenario, on the other hand, as for the particle physics of inflation, we have an axion as the photon, which is embedded in a left-right symmetric model beyond the standard model, and the axion is coupled to SU2 right gauge field. Since now this gauge field in inflation is active, it can source gravitational waves, and it leads to chiral non-Gaussian gravitational waves, which makes it testable. And the source of baryon asymmetry is actually spontaneous CP violation in physics of inflation, because now both parity and CP are violated in physics of inflation. If the lightest right-handed neutrino is the dark matter, then its mass is around 1 GeV, which leads to gamma ray radiation by the radiative decay. This scenario leads to simultaneous baryon and dark matter production in inflation, and as a result, it can explain the coincidences among cosmological parameters. Thank you, I'm done.